Alright, in this video I'm going to be working the Form P's of the Unit 3 quizzes for multivariable calculus. So, let's start off, oh yeah, this is 3-1, just like double integral computation, just like very straightforward double integration. Here's region R, find the double integral of 2x plus 2y dA. Alright, so x going from -1 to 3, y going from 1 to 2, 2x plus 2y dx first, because that was -1 to 3, then y. Alright, with respect to x, an antiderivative would be x squared. Antiderivative for 2y would be 2y times x. We're going to let x run from -1 up to 3. And so that's going to give me 9 plus 3 times 2 is 6y. Minus, when I plug in x equals -1, I square that, I get +1. Plus 2 times y times -1, that would be minus 2y. Alright, so 6y plus 2y is 8y plus 8. So I'm integrating from 1 to 2, 8y plus 8 dy. And yeah, I do recognize a single integral that you could put through a calculator, but I think I'm just going to do these all by hand. 4y squared plus 8y, y going from 1 to 2. And then that would be 4 times 4 is 16, plus another 16, minus 4 plus 8 is 12. That would equal 20. I'm ready to move on. Oh, whoops. Let's see. Let's scroll. I don't usually use this program. It's 2 fingers. Okay. So here's a double integral. We're going to compute it or show that it diverges, and we're going to justify our answer. Okay, I don't see anything wrong with this, so I'm going to do 1/2 y squared. Y equals 0 to y equals 12 divided by x. Okay, so that's 1/2 of 12 divided by x squared minus 1/2 of 0 squared. So that would be 1/2 of 144 over x squared. So I think it's 72 over x squared. So I'm integrating 10 to infinity on 72x to the -2 dx. So I'm going to need an antiderivative. Add 1 to the power, divide by the new power. Okay, so that's -72 over x. As x goes from 10 to infinity, this is where I'm going to need a limit, right? This is not really a real number, so I need to, account for that by taking the limit of the integrand. So, I mean the antiderivative. So the limit as x approaches infinity of -72 over x minus -72 over 10. As x approaches infinity, this fraction here that's circled in red, it's going to go to 0. So that's going to be 0 plus 7.2, and that's just going to equal 7.2. All right. And then, oh, whoops, scrolling. Okay, rewrite the integral with the integration order dx and then dy. All right, so we're going to need to draw a picture of the region of integration. Oh no. Don't need a Google Assistant right now. I still don't need an assistant. What I touched made that happen. But I'm looking at the inside bounds of integration, y equals 4 and y equals 2x. Okay, so since it starts at 4, that does mean that y equals 4 is the bottom of my region. And then y equals 2x, that's kind of a steep line. Y equals 4 to y equals 2x as x goes from 2 to 3. Okay, that is x equals 2 here, so x equals 3 would be over there. And so that is going to be my region of integration. And I'm hitting with some highlighter there. It's just kind of looking worse and worse, but there we go. All right. Now, if I want to do in the integration order dx and then dy, I need to think about a horizontal representative rectangle. Okay, so I might take this thing out and work on it a little bit bigger. At the right edge, I've always got x equals 3, right? It's a vertical line is the edge of my region. On the left, I've got y equals 2x, but that's not an x-coordinate. I need an x-coordinate. So I solve for x, probably by dividing both sides by 2. And say, all right, x equals 1/2 y. So on x, the lower bound would be 1/2 y, and the upper bound would be 3. And that's what I need a color for. And, okay, the integrand would be unchanged if I was changing the order of integration. And let's see, what's going to happen? Okay, I'm going to need to think about, I did x first, so y will be second. I need to think about my y coordinates. Okay, y is clearly starting here at 4, but then I've got this upper bound, okay, but I have a formula for finding the y coordinate at a given x, and x is 3, so y is going to equal 6. So that would be as y goes from 4 to 6, and there we would have ourselves an integral with that requested order of integration. Right, now, finding the value of this double integral, I think this should be pretty standard. Antiderivative, okay, 6y to the 1/2, 2/3 of 6 is 4y to the 3/2. I'm going to just mentally check my antiderivative, derivative of 2xy with respect to y is 2x, and then 6y to the 1/2, yeah, like that. As y goes from 0 up to x squared. Okay, when y equals x squared, I'd have 2x times x squared is 2x cubed. And then x squared to the 3/2 would be x cubed, so plus 4x to the 3. Oh, nice. Okay, and then when y is 0, I'd have 0 plus 0, which would be 0. Okay, so I'm going to integral from 0 to 3. 2x to the 3 plus 4x to the 3 is 6x to the 3. Okay, so that would be 6 over 4, x to the 4, x starts at 0, ends at 3, and that's going to be 3/2 of 81 minus 0. 81 times 3 is 243, divided by 2. Okay, here we've got an integral over R. Okay, so just give a sketch of region R. Oh, okay. Okay, y goes from 5 to 7, so I know I don't need any negative y's. X going from 0 to y, maybe I'll see there. All right, so I've got x equals 0. That's the y-axis. That's my left edge of my region. So I'm going to give that a little bit of thickness. Then the right edge is x equals y. X equals y is the same as y equals x, so I'm going to kind of, I guess I know that that's boundary. And then y equals 5 to y equals 7. Okay, y equals 5, that's boundary. So, okay, there, and then I'll put 7 right here. I don't know, that looks about right. And then that will be another boundary, and okay, that is going to be my region of integration right in here. That's bounded by all 4 of those things. Okay, that's a good sketch. Now, let I equal this double integral, what is the value of I? Okay, well, I think that, I don't know, maybe that's like a multiple choice question I've got. I don't know this one. Anyway, oh, maybe I do. Yeah, no, it's, yeah, I know this one. So I'm going to set up the double integral. Y has a variable attached to it, so that has to be the inside variable of integration. Because if it was the outer variable of integration, my integral would end up having variables in it, and it wouldn't be a number. But I know that this double integral needs to just be a number. All right, so 3x plus 2y. We did y first, and then x. We're going to take an antiderivative with respect to y. Ooh. Oh, man. This is rough. I'm missing something here. I don't know if this one is better to reverse the order. Maybe it is, but I'm not seeing it. Plus 2x plus 1 squared. Oh, I'm going to, and then when y is 0, it's zeroed, so that's going to be it. I'm going to actually factor on this. Times 3. Yeah, that is totally the algebraic thing to do. Yeah. 2x plus 1 times 5x plus 1. Okay, so this is equal to the integral from 0 to 6 of 10x squared. 2x and 5x is 7x and 1. All right, and then, oh, this one's rough. Whoa. Let me see if maybe there's going to be some sort of simplification that I'm not seeing. I'm definitely going to take everything to a denominator of 6. Nope, that'll need to be 21 over 6. I don't know if that's going to be the thing to do, but just in case. I'm going for a common denominator. 6 to the third is 216, and so 20 times 216 plus 21 times 36 plus 6 times 6 would be another 36 divided by 6. That's going to be as far as I take it. I'm going to allow you to use a calculator on the unit test, so I think you could, definitely. Oh, no, wait. I don't want to quit. I don't know what that was. Okay, no, that's the end of the quiz. All right, so let's move on. I'm just going to go back to, now we're going to discard those changes and go to quiz 3.2. Just go through all of these. Ask to mark this thing up, and all right, bounded by the curves. What is 3.2 even? Area and volume. Okay, so write two integrals that represent the area of R, one with integration order dy and dx, and one with integration order dx and dy. All right, dy and dx. We'll do y first, and that's a vertical representative rectangle. Okay, this is exactly like one that's on the 3.1 through 3.4 quiz. So if you want a lot more detail on this one, you can go ahead and see that video, the one that's like all 4 of the quizzes combined into a group quiz. I think it's Form H. I'm sure you have access to that. So starting off at the bottom is the curve x to the 4 over 8 plus 1, and then on top I've got y equals x plus 1. The x is going from 0 to 2. Okay, y was on the inside, then x, and if we're talking about the area of a region, we just integrate dA. So integrate dx and dy. So get rid of those. Okay, that's one. For the other one, I'll switch to blue. If we're going to do, oh no. If we want to do dx and then dy, I need to think horizontally first, because x would come first. And that's going to require me to say, all right, I know this is x equals y minus 1. This one would be x equals, subtract 1 from y, then multiply both sides by 8. And then take the fourth root, and it's going to be the positive fourth root because we're over here in the first quadrant where x is positive, and that would become my balance of integration. All right, so x equals y minus 1 to x equals fourth root of 8 times y minus 1. And then those were x coordinates, so dx, and then dy. If I think about my y's, I'm going from 1 to 3, and there we go. Those are two different integrals that represent the area of R. Find the volume under the graph and above the closed region in the xy plane, probably should say. But if we're talking about volume between a graph and above the xy plane, that's going to be just the double integral of that function. So we're going to be double integrating. Bounds remain to be seen, 4x cubed y cubed. All right, so, and really let the prompt clue you in. X equals y. Okay, x equals 0, x equals y. I should probably sketch it just to make sure it's, where I think it is. Okay, x equals y is that line, as we've seen already. X equals 0 is right here. Oh no, it is one of those where y equals 1 up to y equals 2. Well, I guess we don't really need any special knowledge. Like, yeah, it is going to be with respect to x first, 0 to y, and then y going 1 to 2. I guess can't be too safe. dx and then dy. All right, antiderivative with respect to x. Okay, when x equals y, I'm going to have y to the 4 times y to the 3 is y to the 7, minus when x is 0, I'd have 0y cubed. So I'm going to be integrating from 1 to 2 on y to the 7 dy, which is going to equal 1/8 of y to the 8th. All right, 2 to the 8th, 2, 4, 8, 16, 32, 64, 128, 256. So 256 minus 1, and that's going to be 255 divided by 8. Right. Number 3, right? But do not evaluate a double integral that represents the area of this region. Okay, yes, I remember there was a message with this one. This one we have to do y first. We cannot do x first because of the way that the curve here goes up and then down. Okay, it's kind of subtle, but if we tried to go sideways, you know, we'd be having missing curve kind of, or it'd be there and also there. That's not going to work. So we got to go vertically, okay, because that's always going to be consistent. Okay, got y equals x minus 1, and then y equals log x divided by x squared. And then x is looking like it goes from 1 to 2. Okay, on the bottom I've got log x over x squared, put parentheses around that to be as clear as possible, dy and then dx because it's just area. Average value over a rectangle. Okay, that was something I definitely forgot to mention, you know, when I was doing the lesson this year, but okay, hopefully you know that the average value of a function over a rectangle is going to be, we're going to double integrate that function and then divide by the area of the region that we're integrating over. So vertices at the origin, 4, 0, 4, 2, and 0, 2. Okay, so that's my region of integration. There. And all right, so that is a rectangle that clearly has area 8. I'm going to let x go from, I'm going to just do the antiderivative first, so x going from 0 to 4, and then y going 0 to 2 dx, and then dy. So I'd have 3 halves of 16 minus 3 halves of 0. I need to write that. I'm going to integrate that from 0 to 2 with respect to y. 3 halves of 16 is going to be 24. 24 divided by 8 is 3 times the integral from 0 to 2 of dy. And then I would have 3 times 2 is going to equal 6. Okay. And then we're going to use the values given below to approximate the value of this double integral. Okay, 2 messages here. First thing, you've been in my class for a while now. I don't know if I've ever used this notation. This log squared y, oh, it really doesn't like that because it's, oh, pardon me. Here's what I'm trying to say. What other colors we got? We got a yellow color? Okay, cool. That log squared y, that is the same, just like sine squared. That's log of y squared, right? So that is exactly what we happen to need. Okay, and this is going at the fact that if we have an integral where it's f of x times g of y, so the theorem is, I'm just going to copy it off to the side. The double integral, especially if it's, you know, let's just say y1 to y2, x1 to x2, of f of x multiplied by g of y, dx and dy, that's going to equal the integral from x1 to x2 of f of x dx multiplied by the integral from y1 to y2 of g of y dy. And this is something that, it's not the most useful. It definitely is the type of formula that I wouldn't put it on any poster that went in my single variable calculus classroom, right? Because I don't want anybody thinking they can split an integral over multiplication. In this particular instance, you can, and I think it's most useful to go through on kind of some introductory examples and understand why that's the case. Okay, but either way, that's the situation. So this approximation that they want me to get is going to be 0.8 times 25. Let's see, 25 times 8 is 200, divided by 10, that would be 20. Okay, that's my approximation. Okay, and that's the end of quiz 3.2. So I'm going to discard those changes, go back out, and get on to quiz 3.3. Okay, request to mark it up, and all right, we're going to find the value of the integral, and I think these are going to require us to reverse the order of integration. How many are there? 3 of these. All right. So find the value of the integral, show the work that leads to our answer. All right. Yeah, this is, I can't think of an antiderivative for e to the negative 5y squared with respect to y. Wait, okay, that's a little better. But y equals x up to y equals 1. Okay, x going from 0 to 1, that makes a lot of sense. That's my region. Okay, if I want to switch the order, I need to do x then y. So this is x equals 0 here up to x equals y. And then y is going to be going from 0 to 1. And same integrand, negative 5y squared, except the order is reversed. Okay, with respect to x, I would get an x as my antiderivative. Okay, so x equals 0 to x equals y. When x equals y, I get y e to the negative 5y squared. And so I'm going to say, all right, and then when I plug in x equals 0, I get 0. So I'm going to integrate 0 to 1 on y. Let's see, I'm going to leave some room. E to the negative 5y squared. Really what I'm going to want is negative 10y, right? Because that's the derivative of negative 5y squared. So if I multiply by negative 10 on the outside, I should divide by negative 10 on the outside. And then I should be good to go. Okay, so an antiderivative for negative 10y e to the negative 5y squared, I think that's just going to be e to the negative 5y squared. I'm going to sit for a second, look at that, take the derivative of it mentally. E to the thing is its own derivative. Okay, times negative 10y, yes, that works. All right, so negative 1, I mean, I wrote a half, but I meant a tenth. Unless I'm missing something here. No, negative 1/10, yeah, because I made it a perfect match from 0 to 1. And when I plug in y equals 1, I'm going to get e to the negative 5, and then when I plug in y equals 0, I'm going to get e to the 0, which is 1, and I'm going to stop there. Okay, yeah, this one is also identical to one that I put on that group quiz, but who knows what I'm going to do in future years. So, all right, let's see. I'm thinking, yeah, I needed to draw the region of integration on this one. All right, so y equals x divided by 3. That's a line with a shallow slope. Y equals 2 there. Okay, so, and then x going from 0 to 6, yeah, okay, so that is this region right here. If I want to do dx and then dy, I'm going to go like that. On the left-hand side, let's see, I don't remember which node I was working on. On the left-hand side, I've got x equals 0. Okay, not again with this. Left, I got x equals 0. On the right, I've got x equals 3y. And y is looking like it's going from 0 to 2. Integrand's going to stay the same. dx and then dy. So I'm going to have 1/2 x squared. X going from 0 to 3y. So when x equals 3y, I'd have 1/2 of 9y squared. So 9/2 of y squared times 1 plus y cubed to the 1/2 power. When I plug in 1/2 x squared and x is 0, that would become 0. So this is going to be my integrand. And kind of looking more closely at this, let's say, all right, that's going to be 3/2 of the integral from 0 to 2 of 3y squared, which is what I'm more interested in. That's something I can figure out. That's a chain rule derivative. So that would be, okay, I'm just going to have to, I have no more room. I'm just going to spill over into the next one. 3/2, okay, 2/3 of, I think it's going to be 2/3, I'll block it off. So this is really what's inside the integral. 2/3 of the thing in parentheses to the 3/2. I'm going to think about that for a second. Take the derivative of just the thing inside, ignoring that 3/2, because that was just a constant that came from the 9/2 originally. And, alright, yeah, 1 times 1 plus y cubed to the 1/2 power times 3y squared for the chain rule. Yes, I feel good about that. Y equals 0 up to y equals 2. Okay, cancel these off. Say 1 plus 8 is 9 to the 3/2 minus 1 plus 0 to the 3/2, and that's going to be 26. Alright, now we're going to evaluate the integral and show the work that leads to our answer. This one is another reverse the order. Okay, you notice that they're all pretty similar. X equals y up to x equals 2. And then y going from 0 to 2. Okay, so it's this region right here. If I want to reverse the order of integration, goodness, this is really frustrating. I don't like working on this program. This never happens when I use Samsung Notes. If I do vertically first, I would have y equals 0 up to y equals x. And let me think about that. What's going to happen here? Okay, yeah. And x goes 0 to 2, cosine of x squared dy, and then dx. So y cosine x squared, y going from 0 to x. So that's x cosine x squared minus 0 cosine of x squared. So that'll be x cosine x squared. I think I can think of an antiderivative for that. Or you could say I want 2x, and so I can account for that by doing that. And saying, all right, that's going to be sine of x squared, that antiderivative, on the inside of the integral. So 1/2 of the sine of x squared, x running from 0 to 2. I know the sine of 0, but I don't know the sine of 4, so that's going to be 1/2 of the sine of 4. And, whoops, I think that's all for this one, so I'm going to keep it moving. Discard my changes. Let's see, how many more of these do I have? 3, 5, 6, 7, 8. I got it all the way through the end of the unit. Okay, great. So I'm going to just keep going. This could be a long one, though, this video. So find the volume of the solid enclosed by the paraboloid and the plane. I do believe that I have already worked this problem in this video. That was a problem on the 3.1 quiz, so I am going to... Wait. No, it was not. This was another one on the 3.1 through 3.4 quiz. Okay, so I need to make sure that video is private, I think. I think that's not going to be something I'm going to be recycling and kind of build on these quizzes for future years. Leave this one unlisted. The other one's got to go private, though. Okay, so find the solid of the volume enclosed by this one. Okay, to draw this really simply, z equals x squared plus y squared. It is a paraboloid. I know it's got, actual solidness to it because it's a three-dimensional thing, but I'm just going to say that's z equals 9 right there. And so, the volume is going to be, double integral of all of these little volumes right there. So top minus bottom is what I'm saying. So double integral of, on top I've got the plane, minus on bottom the paraboloid. Okay, and then the next step is kind of figure out what's the intersection. Now, the intersection of those two things would be right there, and I am relying on your, spatial reasoning skills to envision that being a three-dimensional object, and that's the intersection. If I want to find the intersection, okay, so really, I guess, double integral over some region that I'm going to figure out based on the intersection of this dA. Okay, because this is the polar quiz, and we will, and so I need to kind of go through my steps on a polar level. Finding the intersection. Set the two things equal to each other. X squared plus y squared equals 9. Okay. Oh, I need to know what that graph looks like. That's a circle centered at the origin with radius 3. Okay. And so in polar coordinates, if I'm thinking about, that it's everything inside there, all right, because it's all of those little sticks moving around between the paraboloid and the plane. And so I want that whole region. This is r between 0 and 3, and theta because it's a whole circle going from 0 to 2 pi. I'm going to remind you that dA is r dr d theta. Okay, so going over here, that means I'm going to be integrating theta 0 to 2 pi. And r from 0 to 3 on 9 minus 9. I have to get rid of the x's and y's, but fortunately for me, x squared plus y squared equals r squared, and dA is r dr d theta. Now I'm going to, because I don't have all that much room, distribute the r over here and call that 9r minus an r to the 3. And then I am going to say, well, no, I'm not going to use a calculator. I want to because I've already done this integral like just a few minutes ago before I recorded this video, but it's okay. As r runs from 0 to 3, so that's 81 halves minus 81 fourths. Minus 0 when I plug in r equals 0. Half minus a fourth is a fourth, so that will be giving me 81 over 4. And so I'm going to just multiply that by 2 pi and get 81 pi over 2. All right, now we want to convert this double integral to polar coordinates, but I don't think we want to actually, evaluate it. All right, I need that to be visible. There we go. So in the xy plane, y is starting at x. I'm going to give, I don't know what that sound was. Something going on in my house. Y equals x up to y equals the positive square root of 18 minus x squared. I cannot imagine why I did this. Okay. That is going to be a circle centered at the origin with radius square root of 18. Yeah, okay, whatever. Y equals the square root of 18 minus x squared. And I might, kind of justify that for you. Okay. And then I'm going to square both sides. Add x squared to both sides. Right? X squared plus y squared equals r squared. That's r going to the square root of 18. So, okay, I don't know. Who knows? Maybe it'll work out real nice. And then x is going to go from 0 to 3. Oh, maybe, it is. It's, so the point 33, yeah, you need that point here, x equals 0 up to x equals 3 on that curve is there. Because the line is the lower bound of integration on y, I know it's going to be, like that is my region. So pretty much it's this piece of pizza where r is going from 0 to the square root of 18. Cool. And and that's 3 root 2. That also makes sense. And then theta is, now I understand why it was 18 minus x squared. Theta is going pi over 4 to pi over 2. Okay, so if we wanted to convert this into polar coordinates, and I need to remember that dA is r d theta, okay, theta going pi over 4 to pi over 2, r going 0 to the square root of 18, which I think that's okay, you know, as long as you can figure out that square root of 18 is the same as 3 root 2, and x squared plus y squared is r squared. R squared squared is r to the 4th, and dy times dx is dA, that's r dr d theta. I think that's a good conversion because it's either that's simplified enough for our quiz, or in multiple choice you're going to know that's r to the 5th times r to the 5th dr d theta. Okay, and now we're going to set up a double integral in polar coordinates that represents the area inside the graph. Okay, well, once again, when they say area, that's just the double integral of dA. So the double integral over region R of dA, where this is the region right here. Looks like, okay, the graph is 1 plus cosine theta. You know, it ranges from the origin out to the edges of that cardioid. So I'm just going to say R starts at 0 and ends at 1 plus cosine theta. And then theta, okay, now this we would need to figure out, does this cardioid trace out its graph on the interval 0 to 2 pi or 0 to 1 pi, and I just taught a whole unit on this in AP Pre-Cal, and I can't remember, so I think it's going to be 2 pi, because, yeah, at theta equals 0, it's r equals 1 plus 1, then at theta equals pi, it's 1 plus negative 1, and that's 0, and then, yeah, r really never goes negative. Okay, yeah, I am convinced that that traces out its graph on 0 to 2 pi. Okay, if you're not, you might need to do more investigation. Okay, integral from 0 to 2 pi for theta, r going 0 to 1 plus cosine theta, and then dA is r dr d theta, right? And if you're remembering, like, oh, from AP Calculus, it's 1/2 r squared d theta, yeah, there you go. Anti-differentiate r with respect to r. 1/2 of 1 plus cosine theta, you know, whole thing squared, d theta. There you go. That's what we got. We just wanted to set it up. So now we're going to find the double integral of x squared plus y squared dA. Just wish they asked about the double integral of dA, then it would be 36 pi and we could just move on, but okay, we're going to have to do a little bit more. In this one, this is a nice region, a nice circular region centered at the origin, r going 0 to 6. Theta going 0 to 2 pi. And, alright, so 0 to 2 pi, integral 0 to 6. X squared plus y squared is r squared, dA is r dr d theta. So I'm going to combine those r's, the r squared and the r, and that will make 3 powers of r. So I'm going to have 1/4 r to the 4th. Oh, goodness, I don't know if I know 6 to the 4th. 216. Oh, that's really pushing it. 200 times 6 would be 1200. 6 times 16 is 96. 1296 divided by 4. Really don't want to use a calculator. I don't like doing long multiplication or long division either. So that would be 648. And 324. That's a number that, you know, is something I'm supposed to know what it equals, you know, some sort of product or power or something. I'm pretty sure that's what I got. You know, if I made an arithmetic error, forgive me, but I'm trying to do this without a calculator. Okay, so that's going to be 628 pi, or 48 pi. There you go. Crisis averted. 648 pi 1296, I think. I don't know. That was a bit of a stretch for my arithmetic skills. All right, that was 3.4. Discard the changes. Move on to 3.5. All right, surface area. All right, we're going to need that formula. I'm going to put that in right here. Surface area over a region, or like of over a region, surface area on a graph over a region. It's the double integral over region R of the square root of 1 plus fx squared plus fy squared dA. And sometimes these are ones we can compute by hand, sometimes they are not. Okay, surface area of the region enclosed by the paraboloid in the plane. Yes, okay, that's one we definitely need. Okay, once again, I'm going to draw the paraboloid like this and the plane like that. Okay, you've already seen me in this video. Find that the intersection was a circle centered at the origin with radius 3. Okay, so we know that the bounds of integration, we're going to need to do this in a polar way. Okay, but, okay, so yeah, I'm going to actually take the derivatives and stuff, and then I'll do the polar conversion later, because I want you to see it's really not scary. It actually helps a lot. So zx equals 2x, which is going to equal 2r cosine theta. Okay, zy is going to be 2y, which will eventually become 2r sine theta. If I do zx squared plus zy squared, I'm going to have 4r squared times cosine squared theta plus sine squared theta. We know that's always equal to 1, so that's equal to 4r squared. And then 1 plus zx squared plus zy squared is just going to be that plus 1. And if I'm double integrating over that region, which I will turn into, polar in a second, that square root is going to become 4r squared plus 1. And then dA is r d theta. And so it's like, oh, I can actually do this one with no calculator. I'm thinking, okay, nope, not those notes. Okay, pardon me on this. This video has been very sloppily recorded, but I don't know that this one's a forever video. So, r going from 0 to 3, theta going 0 to 2 pi, dA is r d theta. We can do a u substitution. In this video, I have not been doing u substitutions. I've just been kind of like going for it with the chain rule, and so I'm going to keep doing that. I want 8r. This antiderivative would be, I'm going to still have the 1/8 and an integral from 0 to 2 pi. I'll just save that for a second later. Antiderivative is going to be 2/3 of 4r squared plus 1 to the 3 halves. Yes, that does work from 0 to 3. Let's see. 4 times 9 is 36, plus 1 is 37 to the 3 halves. Horrible number, I kind of remember that. 37 to the 3 halves. 2/3 of that. Oh, goodness. Minus, when I plug in 0, I'd get 1 to the 3 halves. At least that's just 1. All right, now... 1/8 times 2/3 would be 2 over 24 is 1/12 of 37 to the 3 halves minus 1. Factor that all out because that's a constant, 0 to 2 pi d theta. I'll just multiply the result by 2 pi. So I would have pi over 6 times 37 to the 3 halves minus 1. That's a really bad number, but, that's how we're going to do it. All right, set up but don't evaluate a double integral that gives the area of the surface of the graph of f over region R gladly. Oh, yes, this looks wonderful. So I'm going to be integrating x -2 to 2, y -5 to 5, so that'll be a dy and then a dx. There will be a square root. I should have looked a little bit more closely at the nature of the function. I'm seeing the square root's probably going to be a little longer. Y's first, then x's 1 plus. All right, fx, partial derivative of f with respect to x, 4x cubed minus 4y. Squared plus, okay, fy is going to equal -4x plus 9. Wait. I messed something up. I think this was supposed to, well, maybe, I don't know, maybe it was intentional what I did here, but I'm going to take a step back. I was thinking I worked the test questions not too long ago. That might have been supposed to be a 3y cubed, but either way, I'm going to work it as it's written. 4x to the third minus 4y plus 9x squared. Yes. Minus 4y plus 9x squared. Squared fy would be -4x Okay, there we go. That's a setup integral. Let's just keep going. Find the area of the part of the plane that lies above the square. Yes, I really like these problems. There might be a better way to do them, like with geometry or something, but the double integral technique, I think it's pretty nice because it's very computable. So what we're going to want to do is get z as a function of x and y. So that's going to be 18 minus x minus y. So my partials are going to be -1 and -1. So when I go to integrate, if I look, this is kind of a unit square. Okay, there's my region of integration. Okay, the square root of 1 plus zx squared plus zy squared dx and dy. Okay, that's the square root of 3. I can factor that out. That's just the double integral over r of dA, so I can multiply the square root of 3 times the area of the region, and that's just going to be square root of 3. Okay, I could bump this problem up in the difficulty though, right? I could make it 2x plus 4y plus z equals 18 and make the square bigger, or like a rectangle that we know the area of. I could do it over a circular region where you could, I could really bump this problem up, and I'm pretty sure I will in the future, but at least for, if you're watching this video this year, you're safe. I think on the test I did bump it up a little bit. It's not a unit square, it's some other kind of square, and maybe one of the x and y has a multiplier or something, so just be aware. It's not just going to be square root of 3 times 1 always. But I've got a bunch of problems that are like this. Okay, that was 3, 5. We're starting to get closer. Getting really hungry. I might have to take a break for food. But I will. Maybe I won't have to. These are triple integrals. This is just computation. 1, 2, 3, 4 triple integrals. 2 I'm not even supposed to compute. I can do this. Alright, so find the value. Okay, with triple integrals, we treat them just like double integrals, right? We just start from the inside and work our way out with respect to x. That would be 2x squared minus 2xy plus xz, x running from 0 up to 4. Okay, when x is 4, 2 times 16 is 32 minus 8y plus 4z. And then I've got x in all three terms, so when x is 0, they'll all be gone. And so that's now my integrand. Just erase that and say 0 to 3, 0 to 2, dy, and then dz. Okay, with respect to y, I got 32y minus 4y squared plus 4yz, y going 0 to 3. And so when, again, they all got y in them, so when y is 0, that'll be really nice. When y equals 3, I'll have 96. Wait, no, that was y. It'll just be 96. Minus 4 times 9 is 36. I know how to take that. Plus 4y is going to be 4 times 3 is 12z. Okay, so that's 60 plus 12z dz. And this is one we'll be able to take by hand. 60z as z runs from 0 to 2 plus 6z squared from 0 to 2. All right, that's going to be 120 plus 6 times 4 is 24. Okay, and 120 and 24 is 144. That's my triple integral. Let's keep going. Now we're going to find another one. This one's got variable bounds, but it's really not that different with respect to z. Antiderivative of 3z squared would just be 1z to the third, so x squared y squared z cubed. 0 is equal to 0 at the bottom, and z equals xy on top. All right. Okay. Then z equals xy. If I cube xy, I'll have 3 copies of x and 3 copies of y, so I think that would be x to the 5, y to the 5, minus 0, x squared, y squared. Okay, so wait, no, it should be x to the 5, y to the 5. Right? X squared, y squared times x cubed, y cubed. Yeah. And so I'm going to be integrating 0 to 1, 0 to y, x to the 5, y to the 5, dy. That does not make sense. Y equals y. I think that was a typing error, and that's supposed to be dx and then dy. Okay, that would be the only thing that would possibly make sense. So I'm going to anti-differentiate with respect to x. I am just going to factor out the 1/6, and then it'll be x to the 6th, y to the 5, x equals 0 to y, x equals y. So if x equals y, then I'd have y to the 6th, y to the 5, and that's y to the 11th. So okay, so 1/6 of the integral from 0 to 1 of y to the 11th dy, the integral from 0 to 1 of y to the 11th dy is going to be 1/12. 1/6 times 1/12 is 1/72. All right, there we go. Now, write but do not evaluate a triple integral that represents the volume of the solid enclosed by the graphs of x equals y squared, z equals 0, and x plus z equals 2. All right, I've done a bunch of examples like this, and I have to admit, my energy is waning here. I'm just going to say 0, z equals 0 is going to be the bottom. Z equals 2 minus x is going to be kind of the, in a z world. That'll be top and bottom. Okay, so that's I'm going to do z first. 0 to 2 minus x. Okay, a triple integral for volume would just be triple integral of dv. So dz. Then x equals y squared and x equals... Oh, yeah, and also I know that x coordinate right here, that's x equals 2. Yeah, so x equals y squared. I'm trying to remember if this is going to be... Okay, I'm going to do something kind of cheesy, but it's all right. I'm going to say, all right, x is running from y squared to 2. I don't know if 2 is first and y squared is later. I think y squared would be first and 2 would be later. Dx, and then x equals y squared, so x plus z equals 2. I think that's going to be 0 to the square root of 2. I might be wrong on this one, and if I had one that bounds wrong, I might slap an absolute value on that. This is a type of question that's much easier on multiple choice than with no support, no technology, so I'm just going to keep going. Rewrite the integral using dz, then dy, and then dx. Okay, so we need to kind of visualize the region of integration and then, reorder it. All right, so z is going from z equals 0. Okay, that's the xy plane. Up to z equals the square root of 9 minus x squared. So I might try my best to draw this for you. All right, z equals 9 minus x, square root of 9 minus x squared. Oh my goodness. I'm really getting frustrated with that. And z equals... Why is this even happening? Okay, it's because I'm pressing that center button at the bottom. Okay, I don't know why that is happening now. Where does that? Oh, I bet I know. I bet Samsung knows to disable that. All right, it's like it's a half circle, right? Like y equals the square root of 9 minus x squared. It goes from x equals -3 to x equals +3. But it's kind of like independent of y, so it's going to be one of these things. Right. That's the best drawing I've got of it. I don't really know what it would... Like that, maybe? I don't know. I may have made it look worse, but okay, that's the region of integration is z going from 0 to that, y equals x up to y equals 3. Okay, well, we're looking in the xy plane. I might switch the color to draw the... That was supposed to be my x-axis. I would think that the y-axis, again, wrong app, for the second time, the y-axis would be here, and then the z-axis is like coming up out of that plane. So y equals x up to y equals 3. Oh my goodness, I forgot that all of this 3D drawing was not necessary at all, because I could have just restricted myself to the to R2. Yeah, so I'm just going to do that because it was dz dy dx versus dz dx dy. So the z is going to stay the same, right? So this thing is also going to stay the same. Okay, I kind of feel a little dumb now, but that's all right. Okay, y equals x, y equals 3, x going from 0 to 3. Okay, I'm going to reverse that to x then y, x equals 0 up to x equals y, like we've done so many times in this video. X equals 0 up to x equals y, y equals 0 to 3. The inner bounds remain unchanged because z stayed in its position. Okay, tangent of z, that's definitely not something we want to anti-differentiate. dz dx dy. Okay, that's better. That makes a little bit more sense. I was thinking that was kind of an advanced drawing for what I expect from y'all. Really pushed my limitations of my art skills. All right, just two more. 3, 7. This is going to be spherical and cylindrical, right? All right, and these are actually really representative of the ones that I want to ask you on the test. So I don't want you to be, wait, no, that's what I wanted. Yeah, I don't want you to be worrying too much about spherical and cylindrical because that is not my focus in my multivariable calculus class. It's something that we do, but you'll do that a lot in physics if you keep taking physics classes. All right, so r theta z, evaluate triple integral over region E of r dv. Oh, okay. This is unfortunate because actually the one that you have to do, I think it's just the integral of 1 dv. So you just find the volume using geometry formulas. Okay, this one will be a little bit more, but yeah, it's all right. So they're just giving us the bounds of integration. I'll do r first, will be 0 to 4, because then it'll be really easy. Theta and z. Alright, so r d theta dz. Wait, yes, because dv is r d theta dz, I need to add in an extra power of r. Ooh, that's tricky. I can see people making an error on that. So it's 1/3 r to the third as r goes from 0 to 4. So 4 to the third is 64. So I'm going to have 64 over 3 times the double integral from negative 2 to 3, 0 to 2 pi, d theta dz. That's a rectangular region in the theta z universe, and so I'm just going to multiply, width times height. That's going to be 2 pi times 5 is 10 pi, so 640 pi divided by 3, and 6 plus 4 is 10, and 10 is not divisible by 3, so I know that does not simplify any further. All right, now find the value. This one, yes, these are spherical, these are spherical coordinates, but there's not really anything for us to do with them besides just take the triple integral, so just don't be scared, is what I'm saying. Okay, antiderivative for 3 rho squared with respect to rho is going to be rho cubed, and then I still have a sine of phi. I like to make my phi's that way, but I bet there's one on the test where I clipped it or something and the phi was written in that way. All right, rho going from 1 up to 4. I'm going to definitely write that to make sure I don't make an error on that. 4 to the third is 64 minus 1 to the third, that'd be 63 sine of phi. Sine of phi d phi d theta. And so that's next step. Antiderivative for sine is negative cosine. All right, so that's negative cosine of pi minus negative cosine of 0. Negative cosine of pi would be positive 1 plus another positive 1. That'll be positive 2. All right, so I've got a 2. Multiply that by 63 and get 126 times the integral from 0 to pi of d theta. That'll give me 126 pi. All right, see, not too bad, especially if we kind of keep our cool and don't get psyched out over the fact that it's spherical coordinates. All right, now here, yes, this is what I was talking about. We're going to use geometry for this one. The triple integral of dv, that's just going to be the volume of E. Right, so now E, it's numbers and spherical coordinates, so it's part of a sphere. rho going from 0 to 2, so the sphere that we're talking about has radius 2. Theta goes from 0 to pi, and remember, like, you know, the sphere is kind of like some up here and then some down there as well. It's a really bad drawing. That made it even worse. But theta is like the theta in that xy coordinate system that's like laid down flat in the plane. So if theta is only going 0 to pi, I'm going to either have the left half or the right half of or basically half the sphere. You're cutting it in half. I wouldn't necessarily say left or right because it's really going to be that half up there that's above the x-axis or beyond the x-axis from our perspective because we're kind of looking at it laterally. Okay, I'm going to get rid of this because it's starting to not look like anything. Okay, I've got half a sphere with radius 0 to 2, but then 5 that was the whole sphere vertically, like that is kind of what I was visualizing now. That would be phi going 0 to pi. So if phi is only going 0 to pi over 2, then it's going to be like that. And I think I only cut it in half twice. So I do think that's a quarter of a sphere. All right, I'm going with that. And if I'm wrong and that's an eighth, let's see, we cut off the left half. It's going to have a 90-degree angle. Theta does go 0 to pi. Yeah, okay, so I think it's going to be a quarter, and it's going to have, like, from the front perspective, there's going to be, like, a wall. And then from the side perspective, it's going to be rounder. It's going to be, like, the back quarter of a sphere. Cut it in half again by virtue of the coordinates. Yeah, I think it's got to be 1/4. Okay, the volume of a sphere is 4/3 pi radius cubed. All right, so 2 to 3 is 8 pi over 3. That's what I've got there. All right, and that's spherical and cylindrical coordinates, right? Not such a huge deal. Something we need to be aware of, hopefully when we have to do it in physics class, you know, in the future, your physics professor is not like annoyed by your lack of experience, or maybe actually impressed by your having experience with spherical and cylindrical coordinates. All right, last one, Jacobian change of variables. Okay, R is the region bounded by these things. We're going to find the double integral of 100 dA. Okay, just want to point out on a strategy level, that's 100 times the area of R. Okay, but I don't know, yeah, this is a parallelogram, and I don't really quite know how to find the area of that. So what I can do is do a Jacobian change of variables. So this is going to be 100 times the double integral over the transformed R, which they already gave us the kind of the transform factors of du and dv, or dv and du. Okay, so really our job is to look, the transformed R will be a rectangle in UV world. We need to figure out what the area of the transformed rectangle is. And then we'll multiply by 100. Okay, but wait, times absolute value of J. Whoops. Yeah, pardon me, I forgot where I was. All right, so I'm going to need something to, yeah, so, yeah, I was thinking I might have been thinking of a problem that was in the practice bank. Okay, I think it's pretty clear that x plus y is going to be either u or v, and then the other one's going to be 2x minus 3y. How would we know which one is which? I think we're going to have to jump in there and do some algebra. So my hypothesis is going to be u and v and v. So if I took 2u plus 3v, wait, no, 2u plus v, that'd be 2x no, 3u plus v. That's 3x minus 3y. Yeah. Okay, and that would just give me 5x. Yeah, okay, I see it. That's right. I can see that. And then u is going from 0 to 3, and v is going 1 to 5. So in the transformed world, I'm just going to say there's a parallelogram. I think, oh no, it's not. It's going to be much worse. Something like that. That's region R. After the transform, this is going to be my v-axis, and that will be my u-axis. U will go 0 to 3, and v will go 1 to 5. Oh, whoops. Cleaning debris off the screen. Okay, and so we'll have this here. That would be 4 times 3 is an area of 12. This is r prime. Then the absolute value of j is going to be, all right, so xu equals 3/5, xv equals 1/5, yu equals 2/5, and yv equals -1/5. I'm going to take that determinant to get j, so j would be -3/25 minus 2/25 is -5/25. So the absolute value of j would be 1/5. So I've got 100 times the double integral of 1/5 du dv over region r prime. Basically, it's 100 divided by 5 is 20 times the area of the region. 20 times 12 is 240. It's a pretty tricky one. All right, find the Jacobian of the transformation. Gladly. Okay. So this one's 3 dimensions, so I'm going to have to take a 3-dimensional or 3x3 determinant, but xu is going to be 5, xv is going to be 0, and xw is also 0. Yu is going to equal 0, yv equals 4, and yw equals, wait, no, yw is equal to 0. I need to slow down. Zu is 0, zv is also 0, and zw, that's what's going to equal 3. Okay, now if I want j, is going to be the determinant of that matrix, and if you were in my linear algebra class, something that we saw is if you have a diagonal matrix, which this thing is because you have all zeros everywhere except for the main diagonal, you can compute that determinant by multiplying down the main diagonal. 5 times 4 is 20, times 3 is 60. All right, happy. Find the Jacobian of the transformation, u squared cosine v, u squared sine v. Okay, we can do that. Xu is going to be 2u cosine v. Xv equals -u squared sine v. Yu is 2u sine v, and yv equals u squared cosine v. Okay, so j, I'm not done with this document yet. I will be soon, though, I think, right? This is the last problem? Yeah. Right, at 1 hour and 8 minutes. Okay, so Jacobian is going to equal 2u times u squared is 2u cubed cosine squared v minus -2u cubed sine squared v. Look at that. 2u cubed times cosine squared v plus sine squared v, which is 1. That's going to equal 2u to the 3. All right, and that's the Jacobian of the transformation, not necessarily the absolute value. The absolute value is what we do when we do the Jacobian change of variables for an integral like we did on number 1. Okay, that was a marathon. That was all of the Form P quizzes. Thanks for watching.